In this problem, we start out with a conductor with a certain charge on it, and we're going to find the potential in the electric field at the surface. And then we're going to hook it up through a conductor to another conducting sphere. Let's start out with just the single sphere. Charge Q1, radius R1. So if we're outside the sphere, because we have a spherical charge distribution, we treat it like a point charge at the origin. So we want the potential at R is equal to R1. That's what we're trying to find. So we treat it like a point charge at the origin. We say the potential due to a point charge is KQ over R. That's for a point charge with V equaling 0 at R equals infinity. And so we say the potential at our point of interest, which is on the surface of the sphere, is K times the charge over the distance. So that's our potential at the surface R1. And remember, this is a scalar quantity. The electric field at the surface, again treating it like a point charge, KQ1 over R squared in the R hat direction. Now we're going to hook this up to another sphere, so we have, and we're going to use a conducting wire to hook them up. So before hooking them up, this sphere has charge Q1 and the other sphere has 0 charge. And after hooking them up, this is I'm going to call it little q1 and little q2. This is radius R1 and that's radius R2. So what this wire does is makes them all one big happy conductor. And that means that every point on that conductor, remember a conductor is an equipotential surface, every point on that conductor must have the same potential. So the potential on the surface of the left sphere, the potential at R1, has to be equal to the potential on the surface of the right sphere. And using the result we got in the first part of this problem, I have K Q1 over R1 has to equal K Q2 over R2. The potential on the surface of one sphere has to be the same as the potential on the surface of the other sphere. We don't know what the charges are yet, though. This charge is going to split. We start out with Q1 on one and 0 on the other, and some of this Q1 is going to go to the other sphere. So this is one of our equations. We have two unknowns. And so I'm going to cancel out my k's, and I'm going to say Q1 over R1 is equal to Q2 over R2. That's one equation. And of course my other equation is that the two charges added together has to equal what I started with. Conservation of charge. Q1 plus Q2, little q1 plus little q2, equals the charge I started with, capital Q1. So what do I get? I just have to do a little algebra. I get Q1 is equal to R1 over R2 times Q2. I plug that into my other equation, and that gives me, sorry, that's Q2 plus Q2, and I end up with Q2 is Q1 over 1 plus R1 over R2, and if I multiply the top and the bottom, by R2 and if I plug this back in and multiply to get Q1, I get R1 Q1 over R1 plus R2. So the question is, what is the potential? We know how the charges split now. We know Q1 and Q2. They want to know what the potential is and what the electric field is. So the potential at R1 is going to equal the potential at R2, and that's going to equal K Q over R1 plus R2. I'm just substituting in my little q, and my electric fields are KQ over R. So on the surface of 1, it's going to be K times its charge over its radius. And on the surface of the other one, it's going to be K times its charge over its radius squared.